automatically does everything inside. But it also using dimensionality reduction so that it will slow down, so that it will increase the speed of the game. So even though you use the deep learning, there also use the dimensionality reduction. To choose which dimensionality reduction technique will be used in the you have to know about the reduction. Then only you can use the deep learning in reducing the dimensionality reduction. So that is all about the introduction about the dimensional reduction. So I hope you got the essence of dimensional reduction. So what exactly it is in the machine learning, and why we need to apply the dimensionality reduction. That is the introduction. Next, I will be dealing with a broad category of the dimensionality reduction. So mainly all the techniques of dimensionality reduction, they fall in two major categories: feature selection and the feature extraction. Okay. In the feature selection is what just we are going to select the subset of all the current features. Whatever number of features are there, so among them we are just selecting, just manually guessing which feature is important to the model or the problem. Okay, which feature is most describing the problem. So manually you are going to select among the features. Okay. For example, say x1, x2 up to xn. These the number of these are the features. Suppose among these you are going to select a subset of this will be the result of the feature selection. Okay. So in the feature selection, you can go to two ways. One is forward selection and another one is the backward selection. In forward selection, what we usually do, we start with the empty subset and we go on putting one by one features selected from the original data. Okay. So it is the initially the output subset is the empty. Then we are selecting from the original one by one the feature and putting in the output subset. So that is a reduced one it is. Okay, that is a forward selection. And second, in the backward selection, reverse way we can do. You take the whole original data, original features of the problem. So remove one by one from it. Okay, and whatever the resulting set is there, so that is the output of backward selection. Okay, nothing. It's a very simple way of dimensionality reduction. So most of us are not using any feature selection. Still, if you have a knowledge about the problem, if you have a knowledge about the model, if you completely understood or describe the problem, everything, if you know it, then you can go through the feature selection. Okay, so you should know about the features and the problem. So in the feature extraction, second broad category is feature extraction. So where it is creating new features, completely new features by combining existing ones. So some existing features already will be there. So you need to reduce those features just by combining the one by one another. So you can see in the example where the output is completely different. The input is x1 up to xn. So where it is the original feature, this has to be reduced. So feature extraction always gives a different set. Okay, a different set which is extracted from the original. Okay, so see y1, y2 is given here, but it is less in the number than your original. So that is some function of data is the feature extraction will give you a completely new data set. Okay, so that is the feature extraction. Among these, you are having two types. Okay, one is supervised and one is unsupervised. Everybody familiar with these two words. where
the
the
dimensionality
dimensionality
reduction happens
happens
in supervised
in supervised
using what
using what
class information
class
available
information
in the data.
available in the data.
So if you
So
are doing,
if you
if
are
you are
doing,
working
if you
with
are
any
working with any
project or if you are
project, or if you are
having the data,
having the data,
you
you can see it,
can
you
imagine
can
it.
imagine it.
So
So
usually we
usually
put all
we
the
put
feature as
all
a
the feature
column
as a column,
and the rows will be
and
the
the
number
rows
of
will
the
be the number of
samples.
the samples.
Okay.
Okay.
So the last
So the
column
last
whatever
column,
is the
whatever
class
is class
information or the
information or the
target
target
information. So
information.
if you are
So
working
if you
in
are
any
working
image
in any
processing
image
or
processing
any
or any
machine learning project,
machine
you
learning
can
project, you
imagine
can
this data
imagine
set.
this
So
data
where
set where
uh,
uh,
the rows
the
are called as
rows are called
samples
as
and the
samples, and the
columns are called
columns
as
are called as a
the dimensions of
dimensions
features.
or
And
features,
the last
and the
column will
last
be
column
what?
will be
It is a
it
target
is a
information
target
or the
information
class
or a
information.
class
Okay,
information.
that information
That
is used
information
to
is used to
it will
give
give
you
you the
the
level of each
level
of
of
the
each of the
sample. By
sample.
seeing
By
that,
seeing
you
that,
can say
you
that
can
this
say that
sample
this
belonging
sample
to this
belonging to
group.
this
So
group.
that is
So
what the
that is what the
supervised
supervised
data is.
data is.
So in the
So in the
supervised, if
supervised,
we use
if we
that class
use that class
information to
information
extract
to
the
extract the
features,
features,
okay,
okay,
then
then it
it is
is
a
a
supervised feature
supervised feature
extraction.
extraction.
Okay.
Okay.
If you do
If
not
you do
use
not
any
use
class
any class
information,
information, even though
it
it
may be there in
may
the
be there
data,
in the
it may
data,
not be
it
there
may
in
not
the
be there
data,
in the
but
data,
if you do
but
not
if you do
use
not
any
use
class
any class
information
information
in the
in
dimension,
the
then
dimension,
it is
then
an
it is a
unsupervised
unsupervised
technique.
technique.
Okay.
Okay.
So you take
You
any of
take
these,
any of
the
these,
feature
the feature
selection or the
selection
feature
or the feature
extraction.
extraction.
The goal
The
is to
goal
find
is to
such a
find
low
such a low
dimensional
dimension
representation of
representation
data
of data
that preserve
that
the
preserve the
information or a
information or
structure
a
in the
structure in
data.
the
The
data.
original
The original
information should not
information
be
should not
lost
be
and
lost,
the
and the
structure, the
structure,
essence
the
of the
essence
data
of the
should be
data should be
preserved. So
preserved. So that
that
is
is the
the
goal
goal
of
of
any
any
of
of
these
these
two
two
techniques.
techniques.
Okay.
Okay.
So
So we'll move. Okay.
so first we
So
will see
first
the
we will see the
unsupervised
unsupervised
dimensionality
dimensionality
reduction.
reduction.
Okay, where
Okay,
the
where
class
the class
information is
information
not
is
going to
not
be
going
used
to be
for the
used for the
dimensional
dimensional
operation.
operation.
Okay, so one of the
So one of
example
the
for such
example for
technique
such
is the
technique is
PCA.
the PCA.
Okay, the
Okay,
principal
the principal
component
component
analysis. So
analysis.
what
So what
exactly the
exactly
PCA
the
is?
PCA is?
Okay,
Okay,
so here
so here
create the new
create the new
uncorrelated
uncorrelated
variables. So
variables.
here the
So here the
variables are
variable
what? These
are
are the
what? These
feature
are the
sections.
feature.
Okay.
Okay,
So these
so these
uncorrelated variance
uncorrelated
is going
variance,
to
it is going to
form
form
that
that
successively
successively
maximize the
maximize the
variance.
variance.
Okay.
Okay,
It
it
will
will
maximize the variance
maximize the
between the
variance between the
samples which
samples
belong
which
to the
belong to the
different class.
different class.
Okay. So
Okay,
that is
so
some
that is
linear
some
operation
linear
it is going to
operation it
do
is
on
going
the
to do on the
original data
original data, so
so
that
that
it
the
maximize the variance
variance
between
between
the
the
samples in the
belonging
data
to the
belonging to the
different class.
different
Okay.
class. Okay,
That is the
so that
operation
is the
here.
operation
Some
here.
of the
Some
steps
of the
of the
steps of
PCA
the
are there,
PCA
so
are there,
everybody
so
will be
everybody will
familiar
be
with
familiar
this.
with this. So just I will break out this.
So in the very
So in
first
the very
step, you
first
need to
step, you need
calculate
to
the means of
calculate the
all
means
the
of all the
features.
features.
So if
Okay,
you are
so
having
if you are
n number
having
of
n
features,
number of
so
the features,
n
so
means you
n
are going
means
to
you are
take.
going to take.
Okay.
Okay,
The step to
the step to
adjust the data by
adjust the data by
subtracting from
subtracting
each
mean from
dimension,
each dimension, from each
from
feature or
each
from the each
dimension,
dimension,
all the data
all the data
from all the
from
columns
all the
you need to
columns you need to
subtract.
subtract
That
those.
means
That
is
mean
going to
is
adjust
going
the
to
data.
adjust the
Okay.
data.
So
Okay,
after
so
adjusting
after
the data,
adjusting the
next
data,
we need to
next we need
calculate
to
the
calculate
covariance
the
matrix.
covariance matrix.
Okay.
Okay,
So between
so
each
between each
pair of the
pair of the
this covariance
this
matrix
covariance
is what?
matrix is what?
It will
It will
give
give
a
you
variance.
a
It will
variance.
give
It will give a
relationship
relationship between
between the
pair of the
pair of the
dimensions,
dimensions,
relationship between the
relationship
pair
between
of
the
the
pair of the features.
features.
Okay.
Okay,
So it is a
so
square
it is a
matrix
square
where
matrix where if
n
n is the number of the features you are going to
n
reduce,
by
n by
n
n
square
square
matrix
matrix is going to
result.
result.
So
Okay,
that
so
n
that n by
by n
n
square
square
matrix
matrix will give you a
between each
between
pair the
each pair
covariance
the covariance
relationship.
relationship. Okay,
Okay.
so
So
that
that
is
is
the
the
covariance
covariance
matrix,
matrix.
the square matrix.
From this you
From
are going
this
to
you are going to
calculate
calculate the
the eigenvector.
eigenvector. Okay, from that square matrix you are going to calculate the eigenvector. If there are n number of the edges or n by n matrix, okay, so n number of the eigenvector you are going to get when you apply the function on that square matrix to produce the eigenvector. So n number of the eigenvectors are going to be produced, and each vector is associated with one eigenvalue. Okay, so that is the step. So calculate eigenvector and the eigenvalue. Okay. The fifth step, you need to order those vectors, okay, based on their eigenvalue. Okay, from highest to lowest eigenvalue, you need to order the vectors. Okay, this will give you the component in the order of significance. So whatever the eigenvector you are going to get, that itself is called as the components. In the principal component analysis, the word component is what? It is one of the eigenvector in the list. Okay, so first eigenvector, which is highest eigenvalue, will give you a more significance to the problem. Okay, so you can choose any of the you can choose from the first to number of components from it. You can choose two components, you can choose first three components like after step 5. Okay, so once you choose one of the component which is more significance, uh, next step is to transform. Okay, that is, you need to transform the original data to the new dimension, which is a lower one, which is a dimensionality reduction. Okay, so for that you just multiply that eigenvector whatever you have chosen with the original data. Okay, so that will give you a transform data which is a lower dimension. Okay, so these are the steps in the PCA. If you want the calculations in all these, that is how to calculate covariance matrix, how to calculate eigenvalue, eigenvectors. Okay, so one of my YouTube channel is there, smita.cloud. So where you can have me, I have explained each and every step mathematically. So since the time was very less, I have not taken any mathematical lessons in any of the technique. So if you want the mathematical essence, so you can go to my channel and check the details of each of these steps. Okay, so just I want to convey you that on what basis the PCA works. So completely on the eigenvector. Okay, that is all about the summary of the PCA where here. So these are all the eigenvectors. One of them you are going to choose and multiply. This is the original data it is. Okay, x1, x2, x3 up to xn is the original data. So where you are multiplying one of with the one of the eigenvector, and it is going to result y1, y2, yn, which is a reduced one. This n, this m, that is a dimension of result, is less than this n. Okay, so you can see. So all the eigenvectors, whatever you put, are all the components, principal components. Okay, among them, principal is which one? Which has a highest eigenvalue. Okay, if I take a first one and the second one are the two components. So here, if this is the original data, so there are, you can visualize these two components. This is the first component and this is the second component. So all the components are orthogonal to each other. Okay, all the components are orthogonal to each other. So this is why this is what the first component, which is principal, so which is got a highest eigen value. Okay, so you can visualize that why it is principal. It is going to fit each and every samples in the dimension. So these dots are called as a samples. Okay, so it is going to this line, this component is a principal component. Why it is principal? It is going to fit, it is going to be treated as a model for this whole samples. Okay, so second technique I have chosen is supervised dimensionality reduction technique, LDA, that is a linear discriminant analysis. Okay, so it uses some class information. Okay, it completely works from the clusters. Okay, it is going to form the clusters while reducing the dimension. Okay, so why it is supervised? It used that class information to form the cluster. The very important aspect of the LDA is it works on the clusters. Okay, so after getting the cluster, it is going to it tries to maximize some criteria. Okay, it tries between the clusters. It is going to maximize some criteria, and within the cluster it is going to minimize some criteria. So what is that criteria? It may be anything. Okay, so that may be any distance. You can choose a Euclidean distance, you can choose a Manhattan distance, you can choose a geodesic distance. It may be any distance, but LDA uses the uh, different what but criteria need to be maximized and need to be minimized. Okay, so these are the some in the diagram you can see here. So x and y are the what the original features. Suppose if I apply any other method without any class information, these are the samples belonging to the one class and these are the samples belonging to the one class. If I transform these samples in one of these feature, okay, suppose y from xy, the result of dimensional reduction is y, suppose. Okay, so when I transform all these samples on this dimension, there is some overlapping. Okay, you can imagine when I transform all these samples on only this y, so you can imagine there is a overlap between the samples. Okay, or when I uh, if I choose x as my reduced dimension, when I transform these all samples on this x, again there is a overlap between the samples. Okay, so that is the drawback behind the feature selection or the PCA, which does the linear combination, which do not use any class information. Okay, so here what it does, LDA will choose such a dimension. LDA will choose such a projection line. In that line, there is much less overlap. Suppose this is the one line which is got from the LDA. This is the projection line or a dimension, reduced dimension got from the LDA. Suppose when I project these samples on this line rather than X and Y, you can see that the overlapping is very much less here. Okay, these samples belonging to one class and these samples belonging to one class. Okay, so how it does? Okay, so it minimizes the distance between the two class. It maximizes the distance between the two class. So that is between this and this, the distance is going to be reduced, and the distance within the class, the samples distance within the class is going to be reduced, and between the class is going to be increased. Okay, so for that reason, the overlapping has been reduced using the LDA. The first step in the LDA is same thing. Calculate means of each dimension, that is calculate the means of each feature for each class in the data. Okay, suppose 5 samples belonging to one class, only for that 5 samples for each dimension you need to calculate the mean. Okay, suppose there are two classes are there in the whole data, so two means you are going to get mu1 and mu2. Again, each mu1 is what, mu1 is what, it is a mean of each dimension in that samples in that data. Okay, suppose n number of features are there. For a first class samples, this m1 is 1. Okay, like that mu2 is also that. Okay, second step, cluster wise adjust the data by subtracting corresponding means. Okay, same, this step is also done in the PCA, that is adjusting the data. Now you have to do on doing on the whole data, the same means of each dimension we have used there. Now from each samples you need to select and corresponding means you need to select and adjust the data. Okay, so that is the second step. Next, third step is calculate within class scatter matrix. Okay, the third step, calculate The scatter matrix is the one where it will show the information of distribution of the data. Okay, so you need to find the scatter matrix within class scatter matrix here. So how many classes are there? So that many scatter matrix will get. How many clusters will be there? That many scatter matrix are going to be calculated, and at the end you are going to add all the scatter matrix to form a one scatter matrix within class scatter matrix. Okay, so how to find that scatter matrix? Using this formula, where x is the feature set, mu I is that particular cluster's mean it is. Okay, so you need to subtract, so adjusted from the adjusted data itself, this matrix you are going to get. Okay, multiply this with what, with the transpose of the same. Ni is the number of samples in that cluster. Okay, so this is what one matrix you are going to get. Okay, that is the SWI. Okay, so fourth step is calculate within class scatter. What this is within, this is between class. Some mistake is there. This is between class scatter matrix. Okay, the formula of that is this one. Okay, this is again one matrix. This is again one matrix. That means the means of the class 1 and the means of the class 2. Uh, so multiply this matrix with the transpose of this matrix. You are going to get the SP. Okay, next, using SW and SB, so you need to apply the inverse. This is not -1, this is the inverse of within class scatter matrix, multiply with the between class scatter matrix. Okay, so you will get one square matrix called M it is. Okay, then you need to apply the same eigen decomposition, that is finding the eigenvector from it, and when you get the eigenvector, again you need to arrange those eigenvector based on the eigenvalue. So it will give in the order of the significance some features it is going to give. So that is what the LDA is. Okay, so if you do not understand any of these mathematics under this, okay, no need to worry. So I have explained each and every uh, formulas, each and every calculations mathematically and interpretation, everything. So it is in my channel Smita Gaur, so you can go through it. Okay. Okay. So next is, so till now whatever we have seen, that is LDA or the PCA, they mainly work on the linear type of the data. Okay, so nowadays the data is much more unstructured, so that we call it as a non-linear data. So one of the example of the non-linear data is manifold data. Okay, so I have taken the manifold data which is non-linear. So where you can see in the diagram, uh, somewhat spiraling structure is there, somewhat spiral structure is there. Okay, so these are the samples belonging to one class, these are the samples belonging to one class. Like this, you are having a number of the samples here in the diagram, so which is completely unstructured, which contain many folds within it. In the spiral, many folds within it. Okay, so in such a non-linear dimensionality reduction methods, they are useful to analyze the data. Okay, uh, so if you are having knowledge in the image processing, okay, so there the some image is there, suppose physical objects are there in that image, then this when I represent that using a data, so this is the representation of such type of the data. You do not know where each sample present in such type of the data, you cannot imagine or visualize that, which is very unstructured data. Okay, so some of the examples dealing with such data type, data are MDS, LLE, ISOMAP, etc. Leave it. See here, when I apply the PCA on this type of the data, the result of PCA is like this. Okay, so you cannot make a separation between between the samples. Okay, all the samples belonging to some class and all classes are overlapping one another. So that is what when we apply the PCA type of the techniques, which is linear, which works only on the linear type of the data. So when I apply those techniques on this type of the data, the result is somewhat like this. Okay. So if you apply any of the nonlinear type of the dimensionality reduction techniques such as MDS or LLE, so I have used the LLE here on the this nonlinear type of the data. See the difference here. See the difference between the PCA and the LLE. So here the separation between the classes is more here. Okay, overlapping is very less here. Okay, so that's what other techniques have been defined for this type of the techniques. Okay, so mainly the nonlinear data reduction techniques, they mainly work on distances. Okay, they mainly work on distances like Euclidean distances, k nearest neighbor, geodesic distance between the data which we are going to consider. Okay. Okay. So some examples are there. So within the nonlinear data. Okay. So how to reduce the dimensions when there is a structure of nonlinearity within the data. So I have taken two examples. Just I will brief out the MDS and the isomap. MDS is what? Multi-dimensional scaling. Okay. This technique mainly we apply when there is a nonlinear and it is supervised one. Okay. Why it is supervised one? While while doing the dimensionality reduction, it uses the class information. Okay, so it mainly work on the distance. Okay, so it is going to construct the square matrix. Like, so we have constructed the covariance matrix in the PCA. We have constructed the uh, in the LDA we have constructed the what the scatter matrix, which is a square matrix, and here in the MDS you are going to construct the distance matrix. Okay, between the pair of the samples you are going to calculate the Euclidean distance and putting that distance in the square matrix. Okay, so again the same thing, the eigen decomposition you are going to apply on the square matrix. Okay, so every technique they differ in the second step, constructing the matrix. After that there will be a eigen decomposition, order of the components, and choosing one among them as a new dimension. Okay, so so isomap is also what it is, a non-linear supervised DR technique. Okay, it is also apply on the non-linear and it is also a supervised technique. Okay, but the difference between MDS and isomap is what? Uh, the distance matrix is what it is using a geodesic distance, not the Euclidean distance. So here Euclidean distance you are going to calculate between the pair of samples. Here geodesic distance is calculated between the pair of the samples and form the square matrix. After that, your same thing, the eigen decomposition is going to be happen. The main thing is what is the difference between Euclidean distance and geodesic distance. Okay, you can see in the this is the data where the structure of data is nonlinear. These are the samples. Okay, structure of data is nonlinear. What is the distance between this A and this B? Okay, the distance between this A and B using Euclidean distance is this one, A to B. What it does, Euclidean distance is what? This is the Euclidean distance. What is the geodesic distance? Between A and B, the Euclidean distance, just you are going to apply the Euclidean distance formula between A and B directly. Sample A and sample B, between those two you are going to apply Euclidean distance and form the distance, that is the A and B. Okay, is that the actual distance between A and B? No, it is not the actual distance between A and B. This is the actual distance between the A and B. Okay, so this actual distance can be found using the geodesic distance. Okay, so what the geodesic distance will do, from A to B, it will use the intermediate samples. It will take the near sample. Again, in that near sample, again it will take another layer sample. Like that, it is going to form a path between A and B. That is, distance is going to be calculated from this sample to this sample, this sample to this sample to this. Like that, yeah, it is going to calculate each and every distance, and this between this A and B, the sum of all these distances will be the geodesic distance. Okay, so that is what the isomap, that is a MDS next version is the isomap, just distance is going to be changed. Okay, so like this you are having other techniques also. LLE, I was talking about the LLE. So what the LLE, again it is going to construct the distance matrix itself, that is, but what is the distance? Nor Euclidean distance nor geodesic distance, the nearest neighbor distance it is going to use. Okay, so that I will I will talk about that later, about the LLE. So next slide, it is moving very slow. Okay, so we have talked about what. Okay, so we have talked about the details of many of the techniques. Okay, so now we will see which are all the facilities available in the Python to apply all these. Okay, so we have used the sklearn library, a Python library where you can have directly the function on the PCA, directly you are having a function on MDS, isomap. We have seen the working of all this, so you need not to implement each and every step of each method. So directly you can have a functions in the sklearn library. Okay, so from the sklearn, the decomposition, import PCA, you are having three versions of the PCA in the library: normal PCA, incremental PCA, kernel PCA, sparse PCA. Okay, so next, for manifold data, that is non-linear data, you are having MDS and the ISO map. Okay, so these are the small snippets from the that library. Just the name of the function is MDS, the name of the function is isomap. Another one is locally linear embedding. Okay, so that is also non-linear. So you can have the directly functions in the sklearn. Okay, so I will take one example, that is PCA. I will take, and I have used that as a PCA for one of the data. Okay, the most common data, that is iris data, where the plants belonging to different species using the original data are originally the dimensions are like this: the sepal length, sepal width, petal length, and the petal width. So based on these features, each sample belonging to one of the class. So this is the data containing 500 samples, I think. Just I have taken the first 5 samples from that data. So all those first samples belonging to the Setosa class here. So I have applied the PCA on this data. Okay, this is the original. Now you can imagine. Now you can be clear with the dimension. These are all the dimensions I need to reduce. Okay. So when I plot all the 500 samples using the using these two features. Okay, if I take x-axis as this and y-axis as this, and these are the samples I have plotted using these two features, you can see the visualization. You can see the visualization of the samples here. Okay, So when I apply the PCI on this data, when I apply the PCI on this data, these are the transformed. There are four dimensions. This is the class information. It is not a dimension. There are four dimensions here. So when I apply the PCA, so just these are the three samples. From the four samples, I have reduced it to three samples, which may be the PCA combination of all this. I got what? Three more new features. Okay, three, not more. Complete only three features we got. Okay, component one, component two, component three. These are the new feature names. Okay, so when I visualize the data now, okay, when I visualize the data now using these new features, okay, suppose component one and component two are the new two features. When I visualize the data, see the 500 samples, how they have distributed over the space. Here overlapping is there, here overlapping is not there. Okay, that means, so whatever the decomposition you are applying, that will not affect your model. Okay, even if you the information is lost, or even if you reduce the dimension, even if you break down the features, okay, then the model will not, the accuracy of the model will not affect. Okay, but the time, the space, the processing speed, all matters here. That's why we are applying dimensionality reduction. So this is the PCA. So using PCA, so we have this result. So like this, you can call in the, instead of PCA, you can call LDA, you can call MDS. So depending on your requirement, you should call. So I have given the details of each and every, on which type of the data all the techniques work. Depending on that, you need to choose the things here. It is a PCA, LDA, MDS, isomap. Okay, if your data is linear, directly go with the PCA and LDA. If your data is non-linear, you go with the MDS and the isomap. Okay, if you do not have any class information in your data, okay, if your application is to just cluster the data, so you can go with any unsupervised type of the data like the PCA. It does not use any class information. Okay, so that is a Python coding of the PCA test. Okay. So what we have discussed till now, this is the summarization. So dimensionality reduction technique, under this we have seen feature selection and the feature extraction. Under that, forward selection and backward selection. So when you are using this feature selection, so when you completely know about the problem, when you completely have a knowledge about the problem, so when you know about the problem, you can abstract the features. You can select the features and you can use only those features. So at that time, you can use the feature selection. If you do not know any, if you don't bother about the data, whatever you have collected, if you do not know about the problem required data, okay, uh, you can go with the feature extraction, where a number of techniques are there under feature extraction. So all the techniques are again divided into supervised and unsupervised, again under supervised nonlinear. So this is going to tell you the requirement where I can use MTS and isomet and LLE. Okay, so where your data is supervised, that is class information is available. Where your data is non-linear, at that time you can use MDS, isomap and LLE. Okay, like that. Supervised linear, you can have LDA. Like that, unsupervised non-linear, you are having one more technique I have not dealt with it, factor analysis. Okay, unsupervised linear, you are having a PCA. Okay, so this is the total summary, whatever. Okay, so I have prepared one code using the PCA. So just you can, if you're able to see it. Okay, so this is the work, the using Python code. This is the code I have prepared using PCA, that is dimensionality reduction using the PCA it is. Okay, so here number first the data we require. Okay, the iris.csv is the data. Okay, So that data I have read. Okay, so this is the first five rows. So these are the samples and these are the feature and this is the class information. Okay. Okay. So this is when I plot the what to see how the data has been distributed over the 500, how the samples have been distributed based on the sepal width and sepal length. To see that, so you need to visualize it. Okay. So only two dimensions. First, I have taken sepal width and sepal length. Using that, so these are the original data visualized. Again, I have taken a different petal width and petal length. I have taken and visualized data. It is like this. The samples are distributed using the features petal width and sepal length. Okay. So we have seen the data without PCA. So this is the without applying PCA. This is also without applying PCA. Okay. Next, I just want to have what PCA here. Okay, this is from sklearn. I have imported the PCA function, nothing else. Okay, so PC call the function PCA. I just want the first three components of the PCA. Okay, so this transform function will does everything. The fit transform function is there now. It will does everything whatever I have explained the details of the PCA. Okay, uh, so once you decompose it, so this is the new. This is the uh, from the 4 dimension, now it has reduced to 3 dimension, principal component 1, principal component 2, and principal component 3. Okay, from the 4 dimension, it has reduced to 3 dimension. Okay, and when I use these new features to visualize my samples, so this is the result. Okay, uh, these are the new features, principal component 1 and principal component 2, and I have visualized the data like this. This is much far better than your original distribution. Okay, that's why we need to apply the dimensionality reduction. Okay, so this is the sample code. So where I have applied the PCA on the iris data. I hope you got the library in the Python, that is the sklearn. Okay, so why we have to do all this nowadays? The deep learning, it will do by itself. The feature extraction is done by the model itself. Okay, still we require this one because uh, still many people are using the old models like artificial neural network, support vector machine. So everything is every model are going accuracy of every model depends on the feature extraction techniques. Okay, so very much important. If you reduce the dimension, the model automatically, the process of the model automatically speed up. Okay, even though in the deep learning or even though in the conventional neural network, so the dimensional reduction, if you apply, then it will give the better results. Okay, so this is all about whatever I have given the topic. So I hope everybody is satisfied with whatever I have talked. Okay, thank you. If you have any questions, if you have any queries on the dimensionality reduction and the Python implementation, you can.
Good morning, participants. If you have any questions, you can ask, please.
Hello. Hello, madam.
Hello,
Hello.
hello, hello,
This is
sir.
Basaraj Chogla speaking, ma'am. Hello, madam. Madam,
Okay,
in
sir.
deep learning, in deep learning, we need to separately
Okay.
do the dimensional reduction, or automatically it will take care in a deep learning.
Sir, your data is a very much raw it is. Okay. So
Okay.
rather than giving that raw data, if you apply one step or one technique of the this dimensionality reduction,
Okay.
that will not lose any information, sir. So if you
Okay.
reduce it
That
and apply to the deep learning, it will give the better results.
it will improve the accuracy, I guess.
Yeah, sir. Yeah, definitely, sir. Otherwise, it will
Okay,
does
ma'am.
by itself, sir.
But still, if you do the dimensional reduction
Yeah,
and
it's
then
better.
apply the deep learning, it will be better, right? Yes, madam.
Because yes, sir, because the data is very much high, sir. Okay, and time and memory space is very matters here. So if you apply it, then you give it to the deep learning, the information will never lose, sir.
Yes, madam. Thank you.
The it will not affect on the accuracy.
Thank you, madam.
Yeah.
Any other questions from the participants? Any questions? Okay. Anyway, if you have any question, if you don't have any questions, so this material will be shared at the end, as we told you earlier. So even resource person contact number and email ID will also be shared at the end of the FDP. So further in coming days, if you have any queries, you can contact the resource person. And with this, on behalf of coordinators and on behalf of the college, I'd like to thank Smita Gaur madam. She's very dynamic and she's very good in coding. She has made lots of effort to prepare the presentations and delivered very uh, smoothly. So I'm very much thankful to you, madam.
Thank you,
And
sir.
maybe
Thank you very much.
thank you, madam.
Okay.
And
Uh, thank,
the next session again will be continued in the noon at 2 o'clock, madam.
okay. Thank you, sir. Thank you for giving the opportunity, sir.
Thank you, thank you, thank you once and all.
Thank you, sir. Thank you, ma'am.
At 2 o'clock, the session, the noon session will be continued. Thank you. Initially, ಸ್ವಲ್ಪ ಇದಿತ್ತು, ಅದು ನಮ್ದು ಸೆಟಪ್ ಇದಿರ್ತೈತೆ ಅದು. ಚಾ ಕೊಡ್ತಾ ಹೇಳ್ರಿ.
This conference is no longer being recorded.
ಎಂದರೆ ಮೇಡಮ್
ಇದು ನಾಲ್ಕು ಅನ್ಸುತ್ತೆ ಯಾವ